Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSE in Institute of Aeronautical Engineering, Hyderabad. So in this video, I'm going to discuss about the importance and uses of graphs. So the very first thing is that what is a graph actually? So graph is nothing but a abstract representation of set of objects, and this graph is going to be defined as set of vertices and set of edges that is going to be connected between the pair of distinct vertices. So if I'm going to have the graph like this, so there is a 1, 2, 3, 4 is nothing but vertices, and then these are all what we call able to call as edges. So here, these 2, 3 is nothing but vertices, and 6, 4 is nothing but an edge. So this graph is nothing but an abstract representation of set of objects, and this set may be is not nothing but set of vertices and set of edges. So normally these graphs are going to be used in the representation, language representation as well. Suppose if I'm going to have the language like this, so zeros and one, which is going to make the even. So in this one, so I'm going to construct a diagram. So this and one will be the one of the application of the graph. And similarly, if I want to show the concept relationship representation, I have to make use of graphs. And in network topology, also I'm going to make use of this graph for representing different types of topology, like bus topology, ring topology, star topology, and mesh topology, hierarchical topology, and extended star topology. So this kind of topologies also, if I want to represent, I have to make use of these graphs only. So which is where this computers is going nothing but considered as nodes, and then where different topologies like bus, ring, star, extender, star, hierarchy, and mesh. So describing how the printers and then computers and other devices are going to be connected over the network, nothing but the network topology, and then which is also going to be display the layout of wire devices and the routing points. So here, tic-tac-toe problem also going to be there, where we can able to represent this problem in the form of a graph as well. So once the game is going to be used as a graph in game tree form, so the graph related algorithms can be applied, and then how to decide what should be the best path to winning that game. So that should be how to be identified. And so what should be this tic-tac-toe problem? So here we're going to have the set of vertices and nodes. So what I'm going to do, I have to make first one. The queen is going to place in first rank first column of the matrix. I'm finding the solution whether I'm going to get it or not. So I'm going to place the second queen in this position. It is not possible. Here is not possible, and this one is also not possible. Okay, all these cases are not going to be possible. So next what I have to do, I have to go back to the previous step and then change the question. So the first scheme, if I'm going to use it, if I'm going to play what where I have to keep the second queen here, this and all question of possible, and this one is going to be possible. So once like this also, this is also another application where the graph is going to be used. And next one, what should be the degree here? So the degree is nothing but the number of edges at a particular vertex is nothing but the degree. Okay. So in graph 2, so all the vertices are going to be stored in the form of a presentation. And degree is nothing but the number of vertices that are connected to the vertex. And notation, so what is this notation? So in a graph G, which is going to have terms set of vertices, and the representation to should not be represent the edge that should be connected U and I and U J. So what is a graph actually? So graph is nothing but primary set of vertices and edges which is going to be followed here, and then the edge is equal to the graph G1. So these are the vertices V1 and E1, and vertex set should be 1, 2, 4, 5, 3, 4, 5, and edges set should be this one. So the next one, what should be the minimum number of edges in any vertex and diagonal graph is that there should be given equation and 10 minus 1 by 2, where n should be the number of edges in the graph. Next one is that the graph is going to have the 4 vertices and what should be maximum number of edges that can be connected. In a graph with 4 vertices is the one, so where we can be able to maximize the number of edges. So and then the vertex of each vertex of each graph will be shorted by n minus 1 by 2 parallel. So what are the subgraphs of the graph means that, so if I'm going to draw a graph here, so the some components of the graph is nothing but a graph. So a subgraph of the graph G is nothing but it is nothing but the subset of the nodes that are going to present along with this have to be find out the subset where we have to be find out this one, and then we have to place it on the queue. So let us consider under two subgraphs what I'm going to have. So in this one, if I'm going to have the vertices is 1, 2, 3, 4, 5, and it just maybe 1, 2, 1, 4, 1, 5, 2, 2, 2. So let us consider a subgraph here. So from this, I'm going to identify different types of subgraphs. So where we can be able to extract this V3, V5, and V4 is 1, 3, 4, 5, etc. And then next is nothing but the path. So what is the path here? The path is nothing but the path. So what is the path here? So path in the graph is nothing but a sequence of vertices connected by the edges, and the length of the path is nothing but the number of edges in the path. So a path in the graph is nothing but a sequence of vertices connected by a graph. So for if I'm going to have a graph, so what should be the path? So this is the path, right? And then the length of the path is nothing but the number of edges that are entering the path, but that is nothing but a path. So what is a cycle here? So cycle is nothing but whether it is going to be starts and with the same node or not. That should be the problem here. So the path is nothing but a cycle. So if it is going to be starts and with the same node. So simply what I'm going to say that is, so it does not repeat any nodes expected for the first and the last. So what is a graph? So graph also may be a tree, but tree may not become a graph. So graph is not a tree. So hence it is going to be connected to simple cycles. So what is a directed graph here? So the directed graph means a graph which is going to have any kind of direction, then it should be called as a directed graph. And the next one is the degree of the vertex. So there are two types of degrees of each and every vertex on the graph. So what should be the in degree and what should be the out degree. So out degree of the vertex means the number of rows originating from a particular vertex is that out degree, and then in degree means the number of rows pointing to particular vertex is nothing but the out degree. So in this graph, if I'm going to look at this two, So what is the n decrease 1 and out decrease 0, so that's why it should be 0. So now I'm going to consider another thing. So final degree is equal to in degree plus out degree. So notation. So in a directed graph, we're going to represent each edge from ij as ij. So and then the given node is going to be presented as adjacent node here. So what is this notation here? So in this notation, we have different types of you know, applications, like where the edges is nothing but 1, 4, and 3, 4, and edges like 4, 1, and edges like 4, 1, and 1, 3, 3. So the edges is 1, 4, and 3, 4, which is going to be in front of the vertex. And incidence is properly limited to the notation of this graph. So the edges 1, 4, and 3, 4 are said to be incident to the node, and the edges 1, 4, and 3, 4 are to be incident of this node. So what is the directed graph here? A directed path is nothing but a path in which all the arrows point out in the same direction. So the directed path is nothing but a path in which all the arrows point out in the same direction is nothing but the directed path. And this directed graph is strongly connected if the directed path connects in each and every two vertices. Suppose if in this graph we are going to have the three vertices, so all the nodes are connected properly. That's why it should be not strongly connected. Why? Because there is an edge from 1 to 2, and then 2 to 1 is there, and 2 to 3 is there, but there is no direction from 1 to 3. So that's why it should not be strongly connected there. So if you look at this, so there is an edge from 1 to 2, 2 to 3, 3 to 2, 2 to 3. So this kind of thing what can able to call it as a strongly connected. Okay. And then when it comes to the representations of the graph, so here a collection of words and adjacency list. Adjacency list is usually preferred as since it is going to provide some compact way to represent the sparse graphs. And adjacency matrix is an representation is somewhat preferred where you can able to expose it. And adjacency list is nothing but so here it should be nothing but the array of vertices, uh, and then we'll have to find out whether each vertex is adjacent to or not. If it is adjacent, then you have to make it as a common vertex of the graph. And the next one is adjacency list. So what is this adjacency list? So adjacency list means that how do you write it? So adjacency list representation is that so whatever the nodes vertices that are present, so that should be represented in the form of the list. From this, what are the nodes that are adjacent to that vertex you have to find out. So for one, I'm going to have two and then five, whereas from two, I'm going to identify one and five, three, four. So if you look at this adjacency list, so what is the first one is node. So this node, what is the chain that is going to be connected, that is fine. So similarly, I'm going to use the next node too. So then I can able to choose one. And the next one, so if I'm going to consider two, so to do and then two. So in an undirected graph, the sum of the lengths of the adjacency list is 2a since it is an undirected edge, and then u appears in the adjacency list. So what is the weighted graph here? So the weighted graph is nothing but, so where the edge is going to have an associated weight, typically it is going to be given by weighted function. So it tends to work. The adjacency list can be really adapted to represent the weight graphs. So look at this weighted graph here. So the graph V comma E of the graph is weighted graph such that the weight of this, sorry, so not weight, and then it is going to be considered as weighted graph. So the weighted edge UV is nothing but the weighted edge of the. So weighted graph is nothing but where the graph is going to have the weights, and along with the weight we are going to be stored in the form of the linked list. So if I'm going to consider a list, so I have to consider the node along with the weight value. So what should I'm going to consider two the weights, this 2 minus 2 and 5. And then next if I'm going to consider 3, it should be 5, and then 10 is there. So that's what I'm going to use. And next one is an adjacency matrix representation. So in this adjacency matrix representation, have to be assumed the vertices are going to be numbered from 1 to n and in arbitrary manner such that the adjacency list of the graph is going to be considered address of AV. The adjacency matrix of the graph G consists of V by V matrix. So it is going to be filled with ones and zeros if and only if there is an edge connecting between them. Otherwise, it should be zero. So let us consider a graph here. So all the diagonal elements are not zero. So that's why the graph symmetry is said to be finite symmetry, right? So let us consider a graph here. So from this, I'm going to be construct a table, a matrix. So by considering the rows here and then columns. So if I'm going to have the edge from 1 to 2, I'm going to mark it as 1. So and then again I'm going to have 1 to 4. So that's what should be 1. So remaining all should be 0. It is not going to be uh, considered. So next one, if I'm going to consider 2, there is no income, only no outgoing edge, so that is only 5 is there, so that's why it should be 1, remaining all should be zeros. So let us consider another matrix, what I'm going to say. So that should be 3. So if I'm going to consider 3, what are the edges that are connected? 3, 5 and 3, 6. So that's why it should be written as well. Next one is weighted graph. So with the weighted matrix representation can also be used for weighted graph. And G is equal to V comma E is the weighted graph with edge weight and then UV and the edge UV. So which is going to be stored in the form of rows. So weighted graph means that the adjacency list mark is going to be represent only for the weighted graph, and then if G is equal to V comma E, which is nothing but the weighted graph with weighted edges, rows, etc. So let us consider weighted examples. So normally in weighted normal matrix representation, we are just representing zeros and ones. But here in weighted graph, we are going to be represent this as rows and columns, and then we are going to represent the weights in between them. So in 1 and 2, what is the weight that is going to be connected? That should be 6. So sorry, 3. So 3 is going to be connected. Good. And then next one, what I have to do, I have to choose whether what is the weight that is connected from 4 to 3. So 4 to 3 it should be 1. So that's why it should be 1. And then similarly, I'm going to identify what is the edge that is connected between 2, 3, 4, 6. So like this, I'm going to fill the adjacency matrix. Let's see how what is the difference between adjacency list and adjacency matrix here. So the adjacency list means that the graph is sparse, big, and unweighted, whereas the adjacency matrix is nothing but new, uh, new, uh, 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 So the adjacency list means that the graph is sparse and the graph is big and weighted, whereas in adjacency matrix the graph is more to be considered as dense matrix and the graph is nothing but the small weighted. So like this, we are going to have different basics of this graph introduction and then uses and then where we have to be used all these methods which are and then follow it. So the weighted representation also be used for weighted graphs, and this should be the representation. So along with the weights, so we are going to be represented. And the adjacency list, there should be a difference between adjacency list and adjacency matrix. So adjacency list means that the graph is sparse and then the graph is big and unweighted. So where adjacency matrix is not nothing but it should be a dense one and the graph is somewhat weighted. So that should be about graph introduction. So let us consider what is the graph basics and all. Normally, graph is nothing but is representation of objects and it should be put in the form of vertices and then edges, and then where the graph is going to be used in the form of language representation, topology, and then graph representation like problems like tic-tac-toe. And normally in some of the terminologies, what I'm going to follow is the degree here. So degree is main, so the number of edges that are the number of edges that are connected to particular matrix is nothing but the degree. And here in this case, we are going to have three graphs. So all are going to be graphs, and this should be the notation where the graph going to be contains the vertices and edges paired, and then so the graph is nothing but set of edges and A is nothing but set of edges. And the maximum number of edges in any vertex under a graph is going to be given by n into n minus 1 by 2. That is the equation how to remember. And the subgraph I'm going to have, so uh, there should be a subgraph such that that should be a part of the graph. And similarly, if I'm going to consider this should be a regular graph onto graph, and if I'm going to go another part of that, then it should be considered as the subgraph. And then graph is said to be connected if every two nodes has point between them, and path is nothing but a sequence of vertices and nodes, and the length of the path is going to be given by number of edges in the path. And cycling is nothing but a path is nothing but a cycle. It will going to be starts and end with the same node. And the tree is nothing but a graph tree, and which is not going to be. And then directed graph. So directed graph means that which is a diagraph where the edges are going to be represented by arrows. And degree means that there are two types of degrees of vertices in degree and half degree. In degree means some of the vertices, and then the sum of the degree is nothing but. So the degree of the vertex, so there should be the two things in degree and half degree. And notation. Notation means that in directed graph we are going to present an edge from. So there should be incident and adjacent. So incident means quite opposite of that adjacent. And these are the notation example. So we're able to use it. And graphs. So graph is nothing but the graph whose in which all the arrows are going to be pointed in one direction. And then comes to representation of the graph. So graphs are going to be presented in two ways. So first one is the adjacency list and adjacency matrices. So both are going to be referred as uh, sparse graph and then representations of the graph. So adjacency list and adjacency matrix. So what is this adjacency list? Means that so here the graph is going to be prepared in the form of nodes like linked list. So that should why it should be called as adjacency linked list. So here we're going to have another kind of presentation, and weighted graph means that where the edge is going to be associated with zeros, weights, and then typically it is going to represent it as e tends to. So the weighted graph are also going to present in the form of that. And sensing matrix. And this adjacency matrix also going to be represented in the form of a matrix form, and weighted graph is there, and same thing, but instead of representing zeros and one, we're going to represent weight here, and finally the difference. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.